Let's explore together the challenges and frontiers of precision medicine in diagnosing two categories of diseases that are diametrically opposed in terms of genetic complexity. On one side, we have rare diseases, often monogenic. On the other, complex and multifactorial diseases. And in both cases, genomic analysis is rewriting the rules of diagnosis. Let's introduce the concept of rare diseases. They are considered rare because these are conditions that affect only a small number of people. In Europe, this means fewer than one person affected per 2,000. The main reference database is Orphanet, which provides information on more than 6,000 rare diseases. Rare diseases are usually serious, often chronic, and sometimes progressive, and can appear from birth or during childhood. Many have a genetic origin, but not all of them. In fact, they can also be infectious diseases, autoimmune disorders, or rare cancers. In many of these cases, the triggering cause is still unknown. Scientific and medical knowledge about rare diseases is limited and inadequate, and for most of them, there is no effective cure available. People affected face difficulties in obtaining a diagnosis, information, competent professionals, and access to quality care. As a result, many patients experience the so-called diagnostic odyssey, and the search for a genetic diagnosis is often the only way to receive treatment, or at least provide a concrete answer to families. In a context where the speed of information sharing is key to progress, the Undiagnosed Disease Network, a research organization supported by the National Institutes of Health, aims to solve medical mysteries through team science and provide answers to patients and families with rare, undiagnosed conditions. A demonstrative example of the value of this approach is provided by the clinical case of two brothers with MEPAN syndrome, a disease with fewer than one case per million. Here's the scenario. Both parents are healthy, but both of their two children are affected. They sequenced the genome of the entire family and found that a variant inherited from the mother and a variant inherited from the father came together in the same gene in both boys, causing this devastating neurological disease. The gene in question is MECR. By analyzing the databases, they realized that the gene is involved in the mitochondrial fatty acid synthesis pathway, and they understood that they could help the boys' bodies by providing one of the missing elements, lipoic acid. After the first doses, the boys began to improve. This is yet another proof of how knowledge of the genome can create precision medicine approaches. Let's take a look at the 100,000 Genomes Project, a major British initiative that sequenced the genomes of patients with rare diseases and cancer, using whole genome sequencing for a truly impressive number of individuals. What was the result? Well, the results were quite surprising. Through the analysis of the sequencing data, it was found that 25% of the participants were carriers of rare diseases. It was also estimated that 18.5% of the data produced are translational discoveries, meaning they are directly applicable on the clinical side. This success demonstrates that whole genome sequencing is crucial for identifying variants that traditional, more limited genetic tests would have missed, thus paving the way for potential treatments and improving the quality of life for these patients. The success of this initiative set the Genome of Europe project in motion, with the goal of creating a reference genomic database at the European level, starting with 100,000 genomes and aiming to reach 500,000 in the future. A secondary but equally important goal is to build the first European reference genome, overcoming the limitations of current standards and promoting an inclusive precision medicine. Not all diseases are like leukemia, where a single genetic alteration acts as a sentinel event that drives the pathology, or like rare monogenic diseases, where a mutated gene causes the illness with a disruptive effect. For complex and multifactorial diseases, genetic reductionism is not enough. A prime example is cardiomyopathy, a disease of the heart muscle. In the past, it was seen as a monogenic disease, but now we know it's a heterogeneous phenotype. In fact, patients with the same gene variant can have very different clinical outcomes. This is the result of the convergence of multiple endophenotypes, such as fibrosis, metabolic dysfunction, or apoptosis, which act together to determine the disease. Today, medicine is evolving toward a network-based approach to overcome genetic reductionism and focus on the entire system. The concept of a unique molecular network is introduced, which identifies the set of genetic alterations, cellular processes, and specific molecules that characterize the disease in an individual and contribute to the phenotypic manifestation. The creation of these networks not only allows for a more precise diagnosis, but also offers the possibility to develop targeted treatments that act selectively on multiple specific molecular targets. The network could also explain why identical genetic variants, when combined with each other or with other variants, lead to different phenotypes. Imagine that the disease isn't caused by a single broken wire, a single gene that fails, but by the instability of the entire electrical grid, meaning the molecular network that powers the heart. For this reason, restoring the balance of the entire molecular network is the new therapeutic frontier. The main drivers of this paradigm shift are advanced computational tools, such as artificial intelligence and machine learning, which are essential for analyzing and interpreting these complex networks, identifying system vulnerabilities, and suggesting therapeutic strategies to restore their balance. Precision medicine isn't just about genetics. It's systems biology aimed at achieving a healthier and more personalized future.